Hello everyone. Today I bring news that significantly complicates our search for life in the universe. The James Webb Space Telescope has analyzed the atmosphere of exoplanet TRAPPIST-1d, one of the most promising worlds in the habitable zone of its star, and the results are disappointing. Its atmosphere looks nothing like Earth's. Let's break down what this means for our quest to find habitable worlds and why the TRAPPIST-1 system, which generated so much excitement back in 2017, is now gradually losing its status as a prime candidate for hosting extraterrestrial life. In 2017, the scientific community and the public at large were absolutely ecstatic over an extraordinary announcement. A modest robotic telescope located in Chile, part of the TRAPPIST project, Transiting Planets and PlanetSiMal's small telescope, had discovered not one, not two, but 7 planets orbiting a single nearby star. This system, immediately named TRAPPIST-1 in honor of the telescope that discovered it, represented something truly unprecedented. 7 Earth-sized planets, all in relatively compact orbits around a red dwarf star just 40 light-years away, practically in our cosmic neighborhood by galactic standards. But the truly exciting aspect wasn't merely the number of planets, it was where they were located. 3 of these worlds, TRAPPIST-1e, 1f, and 1g, orbit directly within the star's habitable zone. The habitable zone is the region around a star where temperatures could allow liquid water to exist on a planet's surface, assuming appropriate atmospheric pressure. Liquid water is considered absolutely essential for life as we know it. Every biochemical process on Earth fundamentally depends on water as a solvent. Discovering not 1 but 3 rocky Earth-sized planets in the habitable zone of a single star seemed almost too good to be true. The TRAPPIST-1 system is radically different from our solar system in scale, though possibly similar in dynamical complexity. The central star is a red dwarf, spectral class M8, with only about 8% of the Sun's mass and less than 1% of its luminosity. It is small, cool, and faint compared to our bright yellow Sun. Because of the star's low luminosity, the habitable zone lies extremely close to it. The planet TRAPPIST-1d orbits at only 2% of the Earth-Sun distance, roughly 3 million kilometers. For comparison, Mercury orbits the Sun at 58 million kilometers. The entire TRAPPIST-1 system, containing all 7 planets, would easily fit inside Mercury's orbit. This compact configuration leads to fascinating consequences. Orbital periods are extremely short. A year on TRAPPIST-1d lasts just 4 Earth days. Neighboring planets are separated by distances comparable to the Earth-Moon gap in our own system. From the surface of any of these worlds, the other planets would appear as large prominent objects in the sky, much bigger than our Moon as seen from Earth. All 7 planets are remarkably similar in size to Earth. TRAPPIST-1e has 0.92 Earth radii, 1f has 1.04, and 1d has 0.77. This dimensional similarity suggests rocky compositions akin to Earth's, in stark contrast to gas giants or icy worlds. TRAPPIST-1d holds a special place within its system, essentially at the inner edge of the habitable zone, somewhat analogous to Venus's position in our solar system, though potentially with more favorable conditions due to the host star's weaker energy output. Early climate models suggested that, with the right kind of atmosphere, TRAPPIST-1d could maintain temperate surface conditions capable of supporting liquid water oceans. The key would be an atmosphere thick enough to efficiently distribute heat, yet not so dense as to trigger a runaway greenhouse effect like that on Venus. There were also intriguing hypotheses about the planet's possible atmospheric chemistry. If TRAPPIST-1d retained an atmosphere rich in water vapor, moderate levels of carbon dioxide, nitrogen, and perhaps even oxygen, it could be genuinely habitable. Detecting such components would provide compelling evidence of potential habitability, and if oxygen were present in amounts inexplicable by purely geological processes, it could even hint at biosignatures. Characterizing the atmospheres of exoplanets requires truly extraordinary observational capabilities. These distant worlds are tiny and faint, millions of times dimmer than their host stars. Simply detecting them is already a major challenge. Analyzing their atmospheres borders on the impossible with conventional technology. The James Webb Space Telescope, JWST, was specifically designed for this kind of task. Its giant 6.5-meter primary mirror collects light with unprecedented efficiency. Its ultra-sensitive infrared detectors can capture the faint signatures of atmospheric molecules, and its position at the Lagrange point L2, far from Earth's heat and vibration, provides unparalleled stability for long observations. To study exoplanet atmospheres, Webb uses a method called transmission spectroscopy. When an exoplanet transits, passing in front of its star from our point of view, a tiny fraction of the starlight filters through the planet's atmosphere before reaching our instruments. Different atmospheric molecules absorb light at specific wavelengths, producing unique spectral fingerprints. It is somewhat analogous to how sunlight passing through Earth's atmosphere appears red at sunset. Atmospheric molecules scatter blue wavelengths more effectively, but Webb can detect much subtler molecular absorptions, allowing scientists to identify water vapor, methane, carbon dioxide, ammonia, and other species in distant planetary atmospheres. The James Webb team observed TRAPPIST-1d over multiple transits using the NIRSpec, Near-Infrared Spectrograph instrument in prism mode, a configuration that allows for broad spectral coverage in a single observation. The timing was favorable. The star was relatively quiet, with no major flares that could have contaminated the data. Data processing was meticulous, employing a pipeline called ExoTEP, specifically developed for the analysis of exoplanet transmission spectra. Multiple corrections were applied, including adjustments for stellar spots, stellar variability, instrumental effects, and cosmic ray contamination. After all this careful work, the final spectrum emerged, and it was disappointing. The spectrum showed none of the expected molecular signatures of an Earth-like atmosphere. There was no detectable water vapor, no molecular nitrogen, and no oxygen. The spectral profile did not match any models of a potentially habitable atmosphere. Instead of a mild, life-friendly atmosphere, the spectrum of TRAPPIST-1d points to several possibilities, none particularly encouraging for habitability. Possibility 1. An extremely thin atmosphere. The planet could possess an incredibly tenuous atmosphere, essentially a near vacuum, similar to Mars but even more extreme. Surface pressure might be hundreds of times lower than Earth's, completely insufficient to maintain liquid water, even if surface temperatures were theoretically suitable. Possibility 2. Thick high-altitude clouds. TRAPPIST-1d might have a substantial atmosphere, but one that is entirely obscured by dense high-altitude cloud layers. Much like Venus, these clouds would block our ability to detect gases at lower levels, rendering the planet opaque to transmission spectroscopy. If true, this wouldn't necessarily rule out habitability, but it would make characterization vastly more difficult. Possibility 3. No atmosphere at all. The planet could be a barren, airless rock, completely devoid of any gaseous envelope. Similar to Mercury or our Moon, it would be bombarded directly by stellar radiation on its exposed rocky surface. This interpretation aligns with atmospheric evolution models, suggesting that planets so close to active stars can lose their atmospheres through radiation-induced atmospheric escape. Whichever interpretation proves correct, none are favorable for life. An extremely thin or absent atmosphere means a surface directly exposed to stellar radiation, extreme temperature differences between day and night, and no protection against meteor impacts. Liquid water cannot exist without sufficient atmospheric pressure. If the planet has Venus-like thick clouds, this would imply scorching surface temperatures due to an intense greenhouse effect, again, incompatible with life as we know it. The emerging pattern is clear. Planets orbiting active red dwarfs face extraordinary challenges in retaining atmospheres and maintaining habitability. TRAPPIST-1 in particular is a highly active star, frequently producing massive flares that release radiation and charged particles. Over billions of years, this radiation can erode planetary atmospheres, leaving behind barren, airless worlds. TRAPPIST-1d is not an isolated case. The James Webb Space Telescope has already observed TRAPPIST-1b and 1c, the innermost planets in the system, and found similar evidence of absent or extremely thin atmospheres. A clear pattern is emerging. The TRAPPIST-1 planets, despite their seemingly favorable locations and Earth-like sizes, do not possess hospitable atmospheres. This raises profound questions about the habitability of planets orbiting red dwarfs in general. These stars make up about 75% of all stars in the galaxy. If their planets systematically lose their atmospheres due to stellar activity, it would dramatically reduce the number of potentially habitable worlds in the universe. We shouldn't lose hope just yet. 3 planets in the TRAPPIST-1 system have not yet been thoroughly characterized by the Webb telescope: 1E, 1F, and 1G. These worlds orbit slightly farther from the star than 1D, potentially offering greater protection against atmospheric erosion. TRAPPIST-1 in particular is considered the most promising candidate in the system. Optimally positioned in the middle of the habitable zone and almost identical in size to Earth, if any planet in the system has managed to retain a habitable atmosphere, it is most likely 1E. Observations of these remaining planets by the James Webb Space Telescope are already planned, and results are expected in the coming years. Until then, we remain hopeful, though increasingly cautious. The search for habitable worlds and extraterrestrial life has proven to be far more challenging than we optimistically expected back in 2017. The TRAPPIST-1 system, once seen as one of the most promising candidates, is gradually revealing itself to be less hospitable than we had hoped. But science advances as much through the elimination of possibilities as through the confirmation of theories. Every world we study, even those that turn out to be inhospitable, teaches us valuable lessons about planetary formation, evolution, and habitability. We are steadily refining our understanding of which types of systems are truly promising for life. And the universe is vast. TRAPPIST-1 is just one system among billions. The search continues, now armed with deeper knowledge about where to look and what to avoid. The truth about life in the universe will eventually be revealed, one careful observation at a time.